Alright, what's going on, guys? So, this is the question we left off with in the session that we didn't have time to finish. And so, we had more work shown, but I wanted to just go ahead and start from the beginning, just so we could start fresh, see where everything comes from, see what we need to be thinking. So, I'll read off the question real quick. It says, a large evacuated flask initially has a mass of 134.567 grams. When the flask is filled with a gas of unknown molar mass to a pressure of 735 torr, at 31 degrees Celsius, its mass is 137.456 grams. When the flask is evacuated again, so we had an evacuated flask, we took the mass of it, we filled it with gas until it reached this pressure, and then we capped it off, we capped the flask, and we weighed its mass again. Once we did that, we took all the gas out, we evacuated it, like pulled a vacuum on it, however you want to get the gas out. Let's see, and then we did all this at 31 degrees Celsius, so we pulled all the gas back out, and then this time we filled it all the way up till it was full with water. And whenever we filled it all the way up with water, its mass is 1,067.9 grams. The density of the water at this temperature, 31 degrees Celsius, is 0.997 grams per milliliter. Calculate the molar mass of gas assuming ideal gas applies. Alright, so like I said, our methodology with these kinds of questions, first things first we can always do is pull out our units, and then also one of the other things we could do first is figure if something like, for this question for instance, we could go ahead and figure out what equation we want to use. So remember we were talking about in the session, we said the only equation in gas laws that deals with molar mass is density. So we know that density equals molar mass over RT, and molar mass times P over RT. Alright, sorry, shooting from the hip here. Alright, but that is the correct equation. So density equals molar mass times pressure over RT. And so if we want to rearrange it for molar mass, we would say molar mass equals density times RT, because you just take the RT, bring it up, over P. So that's the equation we'll want to work with. So I'm going to kind of write it more out of the way now that we have it. So we know now what kind of units we're actually looking for too, or what variables we're looking for. So we know, I'll just write it over here so it's kind of out of the way. Molar mass equals density density times R times T over P. Alright, so let's go ahead and pull out our units. Let's figure out what units we got. So if we read through this, we see a large evacuated flask initially has a mass of 134.56. So I'm going to say M of F for like mass of the flask. That equals 134.567 grams. Alright, when the flask is filled with the gas of unknown molar mass to a pressure, so now we know pressure is going to equal 735 torr. So pressure equals 735 torr at 31 degrees Celsius, so we know the temperature. And its mass, whenever it's filled with the gas, is 137.456 grams. So we want to know mass of the gas. So right now, this isn't mass of the gas yet, because this is technically the gas and the flask combined. So in order to get just the gas, we'll take this number minus this number, and we already did that in the session, so we've already seen that, and I'll do that in just a second, but let's keep pulling out values. So now when the flask is evacuated again, we pull out all the gas, and this time filled all the way with water at 31 degrees Celsius, its mass is 1,067.9, so we'll say mass of water, and again we don't know that one yet because we'll have to subtract the mass of the flask from that number in order to get just the water. Alright? And then we know the density, so we can also, using density here, we see density relates mass and volume. And if we have mass of the water, we can also find volume of the water using the density. So I'll go ahead and also say volume of water. Now in order to get density, so now if we notice, our question deals with molar mass, well that's what we're looking for, but it has density, R, T, and P. So R we can just look up, right? R will be either on a formula sheet, it will be given, or it's got to be, I mean, because there's so many values for R, it would be just plain cruel to try to make you remember all of them. And so, for instance, so we'll figure out which R value we're going to use in a minute, so I'll just go ahead and write R that was not an R, my bad. Y'all know I do that kind of thing. Okay, so R equals, and we'll figure that out in a minute, once we know what all of our units are for sure. So we can find R pretty easy. That's something we just look up. Temperature, we got right here. We just know for all of our gas equations, we have to convert temperature always to Kelvin. It doesn't matter if it's in Fahrenheit, Celsius, it always has to be converted to Kelvin. And we know that. And then torr, we're going to go ahead and convert that to atmospheres in order just to make smaller numbers. And we'll also see that'll help us out with our R value. And I'll explain whenever we get to that. So the only thing that the question doesn't give us is density of the gas. So we're thinking, well, how am I going to find the density of the gas? Well, we know density is just simply mass over volume, right? So if we had the mass of the gas and the volume of the gas, we can find the mass of the gas just by subtracting those two numbers. And if we had the volume of the gas, which will be the exact same as the volume of the water, because they're both filling the flask all the way, so the max that the water can fill is the same as the max that the gas can fill. So the volume of the water will equal volume of gas. And then so once we have the mass of the gas and the volume of the gas, we just divide those two numbers. That gives us density of the gas. And then we can plug that into our equation. So let's go ahead and start converting and finding our values then. So if we were to go ahead and, let's go ahead and convert 735 torr to atmosphere. So it's in a way that we can use it. So I'll give myself more space here so I can write it down in atmospheres. So I'll write a little arrow. So let's convert torr's 735 torr to atmospheres. Remember, torr is the exact same like millimeters of mercury. So 760 torr will equal 1 atmosphere. That cancels out our torrs, gives our answer in atmospheres. So if we were to do that, let's see, 735 divided by 760 equals 0.967. So we'll say 0.967. And then we go to 3 sig figs because we start with 3 sig figs. So now it's in atmospheres. So let's go ahead and write that over here now. So 0.967 atmospheres. All right. Now let's convert temperature to Kelvin. We can just do that right here. 273. Because Celsius plus 273 will equal Kelvin. So that will be 31 plus 273, which equals 304. So 304 Kelvin. All right, so now we got our pressure and our temperature and the units that we want. Let's go ahead and figure out, we could go ahead and, well, not yet. Let's find the mass of our gas. So I'm going to say right here, I'll do it in a different color. Mass of gas. So in order to do mass of the gas, remember I said we're going to take the mass of the flask when it's filled with the gas minus mass of just the flask. So 137.456 grams will equal this, or sorry, not equal, minus 134.567. So that minus that will equal our volume of gas. And we already did that in class, or in, we already did that. .889. That's going to be grams of, we'll say, gas. So we could go ahead and write that over here now. 2.889 grams. All right, now let's go ahead and do the same thing for the water. So that way we can find volume of the water, which will also be volume of the gas. All right. So volume of water. All right, so the volume of the water will be just this value, 1067.9 minus 134.567. which is going to equal 933.333 grams of H2O. Alright, so now let's use this value to find, here, we can go ahead and write that in. So now let's use this value to find the volume of the water. So the way we'll do that is we'll just take this, start with it. So we'll use our conversion factor, which will be the density, which is 0.997 grams for every 1 milliliter. This, of course, will give us our answer in milliliters. All right, so let's see what that is. So 933.333 divided by 0.997 equals 936.141. And we'll go to 6 sig figs because we got 6 sig figs here. So now that will be in milliliters. So we'll say 936.141 milliliters is the volume of our gas. So now remember I said if we have the mass of the gas and the volume of the gas, we can divide those two to get the density of the gas. So let's go ahead and do that. Alright, so I'm going to go ahead and take this away because we've already found that. And I'm going to go ahead and take this away because we've already found that. Alright, and then I'll take this. If you need to see any of those conversions again, just rewind a little bit. Alright. Okay. I hope that didn't sound mean. Alright. Okay. Let me regain bearings. Okay. So we're going to find the density of the gas. And doing that, we'll take the mass of the gas over volume of gas, which will be 2.889 over 936.141 milliliters. And this will give us a value of let's see, 2.889 divided by 936.141 equals 0.00308.6. And we'll go to 4 sig figs because we have 4 divided by 6. Whenever you multiply and divide sig figs, remember you keep the least total. And so, and then our unit, of course, is grams over milliliters. All right, so now we want to think what all, in order to find our R value now, we want to think what all units are we going to be plugging in here. So if we think about it, we're going to be plugging in grams, we'll be plugging in milliliters, we'll be plugging in atmospheres, we'll be plugging in Kelvin. So we're not worried about any of this anymore. So, and we're not worried about that either. Okay, so we're just worried about this, and then whatever our R value is going to be. So, if you remember in class, we're using the R value for our first example. We used 0.08201, or at least we were supposed to use 0.08201. But here we can't use that because that value has the units in liters for volume. Our unit for volume is not in liters here. It's actually in milliliters. So we have to look through our R values. Again, you can just Google R constants for ideal gas law, and you'll find all sorts of different pictures. And so I see here that the value that relates milliliters to atmospheres to Kelvin, which is what we have, atmospheres, Kelvin, and milliliters, is a value that says 82.05745. So again, that's 82.05745. And again, so the units it says is centimeters cubed, which is the exact same thing as a milliliter. So I'm just going to now that you know that, I'm just going to rewrite that as milliliter. But just know, if you look it up, it's going to say centimeters cubed, exact same thing as a milliliter, times atmospheres, and that's going to be over Kelvin times mole. All right, so now that we know that's going to be the R value we use, so that way our milliliters will end up canceling out, our atmospheres will end up canceling out, and our Kelvin will end up canceling out, and it'll give us moles. It'll give us, more specifically, grams per mole. All right, so let's go ahead and plug all that in now. Here, we still got space. So density, or not density, molar mass. Okay, this board just wants to flip, so I guess it just wants us to do it over here. So molar mass equals density times R times T over P. So let's remember, our density was a value of 0.00, it was like 3086 grams per milliliter. Our R, we said we were going to use that value of 82.05745. And then our T was 304 Kelvin. And our P was 0.967 atmospheres. So these are all the values that we found using our work here. Using our work to find this, we were able to find the density of the gas, and now we were able to plug in all these values to our equation. So let's go ahead and do that now. So we'll say M equals density, which is 0.003086. All right, and then that's going to be times our R, which is 82.05745. And here, that 8's probably terrible. All right, 5, and then that's of course times temperature, which is 304. All that goes over our pressure, which is 0.967 atmospheres. That's going to equal, whenever we plug all this into our calculator, let's see, 0.003086 times 82.05745 times 304 equals whatever, divided by 0.967 equals 79.60879. I'll just stop there. And then, of course, the units for molar mass is grams per mole. All right. And so, remember, it's molar mass is not molarity. Molarity is moles over liter. Molar mass is grams per mole. So, the molar mass of this gas is, well, actually, we can't stop here, sorry. So, we have to figure out how many sig figs we need. So, if we look at our density, we got 4. Our constant, we don't worry about. Here we have 3. Here we have 3. So of course, whenever we multiply and divide, we want to use least total, and that would be 3 sig figs. So if we were to round to 3 sig figs, we would just round to the 79.6. So let me just erase this last bit, and I'll move the unit over, and there's our answer. So grams per mole. Alright guys, so I hope you found this video useful. If you have any questions still, be sure that you send me an email, whatever. And I hope that this helped, and I will see y'all on Monday. So until then, I'm out.